Hi, Parker. Do you need something? Parker?
Oh, can you hear me?
Yes, I can.
All right. Good morning. I do have a question actually. I just did it's quiz 9,
Okay.
and so the question is NH4 plus is a conjugate strong acid, and Br minus is a weak conjugate. Can't say it.
Conjugate.
Conjugate base. What will the pH be when NH4Br is dissolved in water?
Less than 7. Okay.
Okay.
It's basically what we're going to go through today.
Okay, because so when a conjugate strong acid and the weak conjugate base are dissolved in water, does it stay? It doesn't like
So, all right, let's just think about it. Let's think what makes sense, Parker. If you just take away conjugate from that,
yeah,
you have a strong acid and a weak base. What are you expecting the pH to be?
higher than 7.
No.
Or no, lower because it's acidic, so it's lower.
Okay. So now we're going to shove the conjugate in there. Strong conjugate acid, weak conjugate base.
It's
There's
the same thing
still
basically.
yes, exactly. It's
Okay.
and that's why when you make a salt and you have something like that ammonium bromide, okay, the ammonia part can react with water. If the ammonia part reacts with water, then it loses one of its H's to the water to make H3O. Does that make sense, Parker?
Yes.
All right. Which leaves it loses one of its H's. The thing that's left is the NH3, which is a much weaker base than H3O is.
Yes.
Okay, so that's why. And if you have the Br, okay, so that was the acid part of it. That was the cation. If you have the Br can't react with water. Okay, there are some we can flip this. Okay, say we do sodium acetate. Okay,
Okay.
sodium is a weak conjugate base. I'm sorry, a weak conjugate acid, but acetate is a strong conjugate base. All right. So the Na does not have enough in it to steal the OH away from water. Does that
Okay.
make sense, Parker? It can't
Yeah,
do
yeah,
it.
yeah.
So, but on the other hand, the acetate will take the H off of water to make acetic acid, leaving H3O plus. I'm sorry, OH minus. Sorry, OH minus. So the acetate reacts with water to make acetic acid, generate acetic acid, but it also reacts to make OH minus, which makes that solution basic.
Okay.
Is that kind of making sense to you?
Yeah, I just kind of I thought about it wrong, and for some reason I was just thinking like when it dissolved, I was thinking it the opposite way, where like I was like, oh yeah, like strong conjugate acid, and I was thinking make it it would become a weak base, and then yeah, I got it flipped, sort of.
Yeah, that's why if you've ever heard that some salts are corrosive, have you ever heard of that? That if you
I mean,
put salt in like a metal, it'll
yeah,
eventually
yeah.
eat the metal away. That's the reason. It's because they are acidic or basic. Okay,
Yeah, that makes more sense. Thank you.
no problem. Anything else?
The only other one I got wrong, it was when it says in the Henderson-Hasselbach equation,
Mm-hmm.
if the conjugate base concentration equals the acid concentration, what can you say about pKa and pH?
Okay. Here,
And
let me. I'm
you can
gonna.
pull up, yeah,
I'm
you can pull
going
up mine.
to. I'm going to go ahead and write the equation. Okay.
Yeah, I I chose pH is greater than pKa, and I think I meant to click pKa is greater than pH because like
Oh no. They're equal.
They're the same.
Mm-hmm.
Okay.
This is the Henderson-Hasselbach. As soon as I get this, as soon as I get manual in here. Okay, and that's saying that the pH is equal to pKa plus the log of the A minus divided by HA.
Yeah.
Okay, Parker, didn't the problem say A minus was equal to HA?
Yes.
What's the log of 1?
I don't know actually. I did. Is it 0?
Yeah.
Yeah.
Type in
Okay.
log 1, it's 0. So if,
So it's just plus 0.
yes, exactly.
Okay,
So
okay.
So the pH is equal to the pKa. As a matter of fact, that's how they determine pKa. What they do is they make a buffer solution of the conjugate base and the acid. All right. They stick this stuff in water and they stick a pH meter in there and determine what the pH is. If the concentrations are the same, then the pH is equal to pKa. You've determined Ka.
Okay. You know, that one, I just didn't realize that log of 1 was 0.
Yeah,
Because
that's
I looked at it and I was like, oh, well, if this one's plus something, I just assumed it was bigger. That's my bad.
Parker. At least you know logs. You know, there literally is probably about 75% of the class that doesn't.
Yeah. When I just remember like logs, like at first when we were first taught them, like our teacher told us, she was like, it looks really complicated, but they're actually like really simple. Like once you get down to it, like if you just keep it simple, it's all right.
That's what I tried to do. That literally is what I tried to do. But things go sideways.
And other than that, I'm pretty good on everything else.
Manuel, how are you doing? Sorry,
I'm good,
Parker.
Professor P. How are you?
I'm doing fine. You're doing okay with all this stuff?
I am. I actually had like 2 questions on the quiz, if we
Okay.
could go over them.
Go for it.
So question 3, I actually don't have it on me in front of me. I'm on my phone, but
Okay, let me pull it up.
yeah, sorry.
Well, I just have to figure out where I'm at. Okay. Okay. Are you seeing the screen?
I see that you are in your inbox. Yes.
Okay. No, I'm gonna have to stop share and then share screen again. Are you talking about are you seeing my mail screen?
Yeah, from Canvas.
Okay. Hi, Ethan. Araceli, how are you doing?
Hi,
I'm good.
I'm
Okay.
fine.
What am I doing? I'm looking up quiz. Never mind. Okay, it's quiz 9, correct, Manuel?
I think it is, yeah.
Okay,
The one that was due this morning.
that would have been quiz
Yep,
9.
9A.
And you said 3?
Question 3, and then the last question.
Okay, I just went over the last question, I think, with Parker.
Oh, did you?
Yeah,
Okay, so
Oh, we didn't
Really?
do question 10.
we didn't, sorry.
okay.
Question. Did I put these out of order?
Well, yeah. I'm not too sure, but I just seen the
4,
question
5,
right there. It was
6,
the
7,
what is the conjugate
8,
base of
9,
HSO4?
10. Okay,
Yeah, right there. Question 4.
HSO4. Conjugate
H-
base is going to be SO4 2 minus.
Well, I had picked that and it said that I got it wrong.
Don't tell me that, Manuel.
I promise. Because
No, don't tell me. Do not tell me that, Manuel. Now, are you sure you didn't pick HSO4?
you know what? It might have been that. I might have picked HO. I'll go back and look whenever I get the chance. But
Okay.
I'm pretty sure
I
picked
can check that in a second.
Okay.
But literally speaking, I'm going down here, Manuel, and I've got the correct answer picked.
Okay. Yeah. Might have been just
All
me
right,
not paying
I will check on that in a second for you. If you don't mind my showing your grade.
I got a 6 out of 10. It's whatever.
Okay. All right. All right. This is an ice diagram.
Okay.
All right.
So
The
my
pH.
question. Okay, go ahead.
Okay. Actually, it's even less than an ice diagram. It's not even an ice diagram. You can take the pH. You can take the pH is equal to 3.2.
Yeah, the negative 3.2.
No, it's not negative. The pH is equal to 3.2. Then
so you
what
don't
you do is
convert
take
it?
10 raised to the negative 3.2 power.
Yeah, to get the
Right.
H ions, right? H plus ions.
Yes. Okay. All right. So, okay, and it's asking the acetic acid at equilibrium. It is an ice diagram. And I got to copy the information down.
And since like acetic acid is a weak acid, it would we would use the general HA plus H2O equals H3O plus A minus, right? We could have done that.
Correct.
Okay. So like my problem was, or like I guess where I was confused was I didn't know where to put the H, because when you put in the calculator 10 to the negative value of the pH, I got that value. I just didn't know where to put in the ice diagram. I didn't know if it was HA initial or
Okay.
the hydronium.
All right. You're seeing the screen now, correct, Manuel?
Oh yeah, I guess I could have used.
I'm going to use AC just because it's easier for me to write out than C2H3O2.
Okay.
So HAC means acetic acid.
Okay.
Plus H2O. All right. That you're used to that, right?
Yep.
All right. So if I'm going to do my ice diagram, the first thing I'm going to do is that my pH is equal to 3.2, correct?
Yep.
So my H plus is equal to 10 raised to the negative 3.2, correct?
Yep.
Okay. I got 6.31 e to the minus 4.
Yep. That's what I got.
Okay, so that is my equilibrium concentration. That's my equilibrium concentration of my H3O plus, right?
Okay. So, well, see, that's I'm not that's where I was confused. I didn't know if it was on the HAC or the hydronium ions. So that's kind of where I was stuck.
Okay. All right. So it's asking me what this concentration is. And the other bit of information that I have is that my Ka is equal to 1.8 e to the minus 5th. Okay. I've got my, I don't know what this is, right? I've got this concentration 6.31 e to the minus 4th, right?
Well,
right, Manuel?
yeah.
I got this from I got this number from the pH.
Okay.
So
Okay. Yeah. That's where I was confused. I didn't know where to put the concentration for.
that's the concentration of the H3O at equilibrium.
Okay.
But what you have to realize is if I've made 1 mole of this, I've made 1 mole of this.
Okay.
So the concentration of the AC minus and the H3O positive are the same.
Okay.
Oh, okay. I think that's the part I
So you get 1.8
misunderstood.
e to the minus fifth is equal to 6.31
Raised to the second power.
e to the minus 4 times, I'm doing it this way because some people can't see that, Emmanuel. You are right. Ah. Okay. Basically multiply both sides by X and then divide by 1.8 e to the minus 5. So
Wait, I'm sorry. Did you say multiply 6.31 by both sides?
no, you multiply X by both sides
Oh, okay.
and
Yeah,
then
yeah.
divide by 1.8 e to the 5th.
Okay.
And I get 0.0221.
Okay. And I'm assuming that the zero, what was the value? You said something 5.1. That was the value when you multiply 6.31 e to the negative 4th.
No,
Right.
I didn't tell you what that result was. If you need to know it, it was 3.98 times 10 to the minus 7.
Oh, okay. No, okay, that's fine. But I think I did see 0.0. You said 0.02.
I
Yeah,
may have put
221.
0.0223. That may have been the answer.
Okay. Yeah. I think I'd seen that answer. Okay.
All right, but it's close enough to this answer that
Yeah.
I hope you won't begrudge me.
Okay. Yeah, that was my only question. Thank you.
Okay, that was 2 questions, Manuel.
Oh, yeah. The second question. Yeah, appreciate it.
Okay, anybody else have anything?
Uh,
How are you doing on the ice problems?
well, I mean, I thought I was doing good, but then like I got the 2 like ice problems on this quiz like wrong. So
You gotta practice them. You gotta have these down. All right.
Wait,
2
yeah,
questions.
Professor P, I'm sorry, I have a question. So do we normally, it's over this problem. Do we normally assume that in the disassociation of the H plus ions, the equilibrium is going to be the same for the hydronium ion and the AC, like ion?
You have to, Emmanuel, you have to. Unless
Unless the
you are
question tells you
specifically told.
otherwise?
Unless you're told specifically otherwise, and we're gonna go over that today. It's the first part
Okay.
of the next chapter.
Oh, okay,
It's
okay.
basically what happens when you have some conjugate, some common ion already present. And it affects the equilibrium.
Okay.
And we are gonna talk about that today. Jen, did you get your hair cut?
Yeah, I did.
Okay. Looks nice.
Thank you. I've just chopped it all off because I don't know, it's summer and
Because
it's
it's
too hot
summer.
to have it super long.
Well, yeah. Any more questions, ladies and gentlemen?
can you go over 4?
Is it actual question 4 or is it the 4th in the list? Because what I had to do is I had to add take questions away and add them.
Oh,
Is it for this one? The
okay, I'm just
dissolution
gonna
of-
read out the one. It's like NH4 is a conjugate acid, a strong acid, and Br minus is a weak conjugate base. What will the pH be when NH4Br is dissolved in
This
water?
is something you had to read ahead on. Okay. Okay. What are you seeing? Are you seeing the slideshow or are you seeing?
I'm seeing the
the
slideshow
quiz?
right now.
Good. That's where I want you to be. Okay. We're going to talk about this. This is the last part of the acid bases. Have you ever heard that when you put like a salt water into a bucket, it's corrosive?
Yeah.
All right. This is the reason why. Come on. Thank you. All right. We have two things. We have a salt, NH4Br. Okay. I told you NH4 plus is a strong conjugate acid. Br minus is a weak. It's actually weak to a non-existent. Conjugate base. In other words, Br minus does not act like a base.
Okay.
All right. We have Br minus plus H2O. What it's supposed to do is it's supposed to grab the H to make HBr, leaving OH minus, right?
Yes.
Doesn't happen. Br minus is not strong enough to pull that hydrogen off of water. So it doesn't happen.
Oh, okay. So the solution stays acidic.
On the other hand, my NH4 plus water makes H3O plus NH3. All right.
Hmm.
This does occur. Okay. So if the top one doesn't occur and the bottom one does, overall, am I generating H3Os and or OH minuses?
You're generating H3Os.
Okay, if my conjugate acid strength is equal to my conjugate base strength, then when I put the salt in the water, like for example, when I have NaCl, the sodium doesn't act like a conjugate base, and the chloride doesn't act like a conjugate, wait, other way around. Chloride doesn't act like a conjugate base, and the sodium doesn't act like a conjugate acid. Those reactions with water don't happen. So my conjugate acid strength equals my conjugate base. My H3Os and OH minuses cancel out. pH 7.
Wait a minute.
Does that make sense?
Yeah.
All right. On the other hand, if my conjugate acid is strong and my conjugate base is weak, overall, my conjugate acid is producing H3O, but my conjugate base is not producing OH minus. pH goes down.
All right. I understand what I misunderstood about this question now.
We flip that around, guys. If my conjugate base is strong and my conjugate acid is weak, like for the example where I have sodium acetate. Acetate is a strong conjugate base. It reacts with water to regenerate. I know this sounds strange, but it reacts with water to regenerate acetic acid. And you think to yourself, oh, that's generating acid. But it's not really, because the acetic acid is a weak acid. It's generating acetic acid plus OH minus, which is a very strong base. So I'm generating OH minuses. Okay, I'm generating OH minuses, but by the same token, my sodium does not react with water, so I don't generate any H3Os. My acetate generates OH minuses. My sodium does not generate H3Os. It is a basic solution. So literally speaking, some salts will act as acids or base, depending upon what their conjugate acid or conjugate base is. Make sense, guys? Even if it doesn't, you got to live with it. All right, again, I'm going to throw this general question out to you guys. I'm throwing this out to you, and you have to answer it honestly yourself. Withdrawal date is coming up. How much have we spent in determining and using ice diagrams and making that determination? A ton of time, guys. Ask yourself the question, how did I do on the first test? And do I understand ice diagrams? Because if you don't understand ice diagrams, you really aren't going to pass the next test. Circumstances dictated that I give this next test after the withdrawal date. I'm sorry about that, but it was just the circumstances that if I had made it before the withdrawal date, this means I wouldn't have 2 days to talk about chapter 18. And I think we need it. Okay, off the soapbox now. I believe, ladies and gentlemen, that we left off. I got to figure out where we left off. And hopefully it's with that stuff we were just talking about. Nope, not quite this far, I don't think. Yep. Are we all sick of our ice diagrams yet? Are we? Nobody's answering. Okay, good. I can talk more about them. Sorry, I'm trying to figure out where I left off. I've talked about 2 weak acids, right? Jen is at least being honest. I've talked about 2 weak acids. When you have 2 weak acids mixture, forget about the one that's weaker. Have I done the pH of a weak base where I give you the Ka? The key here when you're doing this is you have to realize I have a weak base. If I have a weak base, I can't use a Ka. Let's deal with this problem and continue on from there. I have the pH of a 2.4 molar methylamine solution with a Ka of 2.27. Now, I've got methylamine. Methylamine is a weak base. So what happens when methylamine gets put in the solution? Okay, what happens is at the very end, I'm going to draw it like this, guys, because this is what's happening. That is methylamine. This is how the OH gets generated with methylamine. All right, it's an equilibrium. I'm generating OH minus. What you have to understand is that Ka is going to be equal to my H3O concentration times my A minus concentration divided by my HA concentration. right? Do you see OH minus anywhere in this expression? Does anybody see OH minus anywhere in that expression? So I can't use Ka. I have to figure out what my Kb is, which is going to be equal to concentration of methyl H3 plus times OH minus divided by methylamine. Does that make sense, guys? Conveniently, I have a way to get from Ka to Kb because I know that Ka times Kb is equal to Kw. I take my Ka, which was 2.27 times 10 to the 11th. If I multiply that by Kb, I get 1 times 10 to the minus 14th. In this way, I can generate a Kb of 4.40 times 10 to the minus 4th. Are you with me? Are you with me in terms of what we have to do? And are you with me in how I did it?
Is the 1 times 10 to the negative 14th like a constant?
Kw, yes.
Okay.
Every time you multiply Ka times Kb, you get 1 times 10 to the minus 14th. It's where we generated the other equation, pH plus POH equals 14. Okay, so from here, it's just an ice diagram. But there's another nuance. I ask for the pH. So we're going to solve for OH. When we set up the ice diagram, because my Kb is equal to an OH concentration, I'm going to find OH concentration. Then I'm going to turn my OH concentration into POH. And I know that pH plus POH equal 14. I subtract my POH from 14. I get my pH. Questions, guys? Anybody? Can anybody think of another way I can solve for pH?
An ice table or
No. Instead of solving for pH, instead of doing it this way with that equation, is there another way I can solve for pH?
Once you have the concentration of OH, can you do the negative log, the concentration of OH?
That's how you get POH. That's how you change it into POH.
Oh, wouldn't it be the 10 to the exponent? I'm not sure. I'm just guessing at this point. But I know that it has to do with the concentration of OH.
Concentration of OH times the concentration of H plus equals 1 times 10 to the minus 14th. You can take 1 times 10 to the minus 14th, divide it by your OH concentration. That would give you your H3O plus concentration. Simply then, you take the negative log of that concentration, you get the pH. Either way will work. Setting up my ice diagram. Okay, Sachari. Sachari, you out there?
Yes, I am.
Okay, I'm setting up my ice diagram.
Okay.
Do I know what my methylamine?
Yes.
Okay. Do I know where am I going to put it in this? Let me change this a bit so you may understand it a little better.
Okay.
Okay. Where am I going to put the 2.4?
Mm, would it be below the NH2?
No. Oh, yeah. I'm sorry. Yes. I got to find where is my slideshow? So yes, you're absolutely right. We are going to put it. So Sachari, what is my concentration initially of methyl NH3 plus and OH minus?
It's not given.
So it's not given. Does that mean, damn it, that there's any there?
Right.
So therefore, my methylamine is going to be zero. I'm in a slideshow. That's why I can't edit it. I'm a moron. Okay, so my methylamine is going to be 0. My hydroxide is going to be 0.
Yes.
All right, so what is my equilibrium concentration of methyl NH3 plus and OH minus? What's that going to be?
0.
Equilibrium.
Oh.
Do you know what it is?
No.
Call it X.
Okay.
So if I call the equilibrium concentration of my NH3 plus and my OH minus X, then I've gained X in both of those for the change. I've lost it from my methylamine. So my equilibrium concentration of methylamine is going to be 2.4 minus X. Are we good with that? Sachari, are we good? Do we understand? Does anybody not
Yes.
understand how the ice table got filled out? Manuel just gave me a thumbs up. Anaya, we good? Jessica, we good?
I think so.
Okay. So now I have my equilibrium concentrations. I just have to plug them in to my KB expression. X times X are my methylamine NH3 plus and my OH minus. 2.4 minus X is the concentration of my methylamine. Again, we're going to disregard X because my KB is so much smaller than 2.4 molar. Okay, so I get 2.4 times my KB, that's equal to X squared. The concentration of my X is 0.00032. I check it against the 5% and I am balanced. I have my, from doing my 5% rule, I'm taking my 0.00032, dividing it by the number I subtracted it from. It's 1.4, less than 5. I'm good to go. Are you all with me now? If you're not, stop me.
Yeah, I have a question.
I'm here. Daniel.
You're solving for KB, but do we need to do anything like convert it into KA?
We will we're going to need to do something. I'm going to show you that in a second. Okay,
Oh,
Manuel,
okay, so we're not there
answer
yet.
the question.
Okay,
Answer this question. What is X equal to?
Well, that was my question. I didn't know if we did the
Well,
conversion.
you tell me right now. We just solved for X. What is X? What's that the concentration of?
The OH minus ions?
Can I get a pH from an OH minus concentration?
Yes.
No, you can eventually. Can you do it directly?
Oh, no.
So I have to change my OH concentration into a POH. I do that by taking the negative log of my OH concentration. I get POH is equal to 3.49. All right. I now know the expression POH from plus pH is equal to 14. I subtract the 3.49 from the 14. I get 10.51. That is the pH. Does it make sense? Are we finding the pH of a base? Is that what this problem started out to do? Was to find the pH of a base?
Yep.
All right. If that's what we set out to do, is the pH consistent with being a base?
Yes.
It's higher than 7. It is a base. So when you are given a Ka and you are given a concentration of a base, first step is to turn the Ka into a Kb. Use the concentration of your base to set up your ice diagram. Use the Kb equilibrium constant expression to determine your concentration of OH minus. Turn the OH minus into a POH. Subtract that from 14. That will be your pH. You can also do this by taking, let's see. I want to go home and insert new slide. I got how many zeros in there? 3 zeros. Remember, my concentration of acid, H3O plus, times my concentration of OH minus equals 1 times 10 negative 14. So all I have to do is take my concentration of OH, divide it into 1 times 10 to the minus 14th. Divided by 0.00032. This gives me a H plus concentration equal to 3.1 e to the minus 11. Negative log equals my pH. And I got 10.5. As compared to 10.5. So you can solve it either way, whichever way is easiest for you, solve it, okay? Bonita, who's behind the cage? Who's in the cage, Bonita?
It's a playpen, my son.
It's a cage. At least you don't have a roof on the cage.
Right?
All right. Are we good with that, ladies and gentlemen? We feel fairly confident with that, Natalia? Emily, we good?
Professor,
Yes. Araceli.
on the slide before, I got like a little bit confused on one part. I didn't understand how you got the 3.13 e to the negative 11. Is
I
that
divided 1 times. Okay. That's the concentration of my base, of my OH minus. Okay,
Oh, okay.
Araceli?
okay?
That's, I divided 1, no. This number, does that make sense to you now, Araceli? I
I
took
get-
the 1 e to the negative 14th, divided it by 0.00032, which is the concentration of my OH. That gives me my concentration of H plus. I just take the negative log of that, got the pH.
Okay, thank you.
All right, right now we are going to talk about salts. Anions are bases. What can happen is if my anion is strong enough, it can go ahead and grab an H off of water to regenerate a weak acid, plus what's left of the water is OH minus. Now you got to understand, even though we're generating an acid, it's a weak acid. OH minus is a very, very, very strong base. So when I put this X minus in water, I generate a weak acid and a very, very strong base. So anions are bases. If I have a cation with an acidic proton, like NH4+, what can happen is that NH4+ can shove that hydrogen ion onto water to make H3O plus NH3 straight. So in other words, my NH4+ can act like an acid. If I have a metal cation, the metal cation can grab the OH away from water, leaving H+. So if I have a metal cation or NH3+, those will act to be acids. Anions react with water to grab an H, leaving OH minus. NH4 pluses shove an H onto water, making H3O plus. I'm sorry, NH4 plus grabs an hydrogen and it will, wait. Sorry, I'm losing track here. The NH4 plus will shove a proton onto water, generating the hydronium ion, lowering the pH. If a cation, the cation will react with H2O to grab an OH minus from it, generating H plus, which reacts with water to make H3O plus. Both instances, the metal cation or the NH4 plus, act as acids. So I have to understand that my cation can make an acid, my anion can make a base. Now, if I'm just starting out and I have a strong acid, that will make a weak conjugate base. A weak acid will make a strong conjugate base. They kind of are opposite in effect. Strong acid, the conjugate base it creates will be weak. A weak acid will create a conjugate base that is strong. A strong base will create a weak conjugate acid. A weak acid will make a strong conjugate base. They're kind of opposite in effect. If it's strong on one side, it's going to be weak on the other. Again, we're creating the acid is linked to its conjugate base. All right. If my anion is a strong base, remember, if it's a strong base, it was created from a weak acid. If my conjugate base is strong, it will react with my water to make a weak acid and OH minus. If I just had A minus, Natalia, what would the pH of this solution be? Higher than 7, lower than 7?
Lower.
Lower than 7. Does that mean it's acidic?
Yes.
Okay. Am I generating? This is a weak acid. That's a strong base. Am I generating acid or am I generating base?
Oh, sorry, you're generating the base.
If I'm generating OH, look at it this way, guys. If I'm generating OH, OH is the strongest base there is. If I'm generating H3O, that's the strongest acid there is. So if I'm generating OH minus, I'm basic. My pH is going to be higher than 7. If my conjugate acid is strong, I generate H plus. So Emily, if I'm generating H plus, is my pH going to be higher or lower than 7?
It's going to be lower.
It's going to be lower than 7 if I just had M plus. Now let's consider if I've got a weak conjugate base. It's not going to grab the proton from water. I get no reaction. Do I have any OH minus generated? Leonardo. If I get no reaction, does my W minus generate any OH minus?
No.
No, it doesn't. Same token. If my conjugate acid is weak, do I get any H plus generated? Vanessa.
Do you get any what generated?
If my weak conjugate acid cannot react with water to pull off the hydroxide, do I generate any H plus? I got no reaction, Vanessa.
So no?
No. My P plus will not produce any H plus, and by consequence, my W minus, because it's weak, will not generate any OH minus. So if I have a salt, my salt is made of a weak conjugate acid and a strong conjugate base. That's what makes up my salt. My P plus will not react. I'm not generating H pluses. However, my A minus will react to generate OH minus. Anaya, in this scenario, what am I generating? H pluses or OH minuses?
Sorry, you can't hear me.
No, I can't.
Is it OH minuses?
I'm generating OH minuses. So if I put a salt in the water, my salt has my cation that is a weak conjugate acid. It's not going to react to make H3Os, but my A minus will react to make OH minuses. So I put a salt in the water, I make a base. Does that make sense to you? Have you ever heard of salt being put into something and it being corrosive? It's kind of like, has anybody ever heard about the salt that they put on the roads up north in the winter? It's corrosive to cars. This is the reason. They're using a form of the salt that has a weak conjugate acid and a strong conjugate base. Therefore, that salt is corrosive to the automobile. All right. Now, if I pair the other one, a strong conjugate acid with a weak conjugate base, what's going to happen is my cation can react with water to generate H pluses, but my anion can't react with water, so no OH minuses are generated. So if I'm generating H pluses, but not generating OH minuses, Jana, what's the overall effect on my pH? Jana, shake your head to see if you understand. I'm not hearing you, Jana. Hit your mute button.
Can you hear
Talk.
me?
Yes, I can hear you now.
Can you please repeat the question?
I have a salt. My salt consists of a cation that is a strong conjugate acid, but the anion is a weak conjugate base. My strong conjugate acid produces H plus. My weak conjugate base is not strong enough to produce any OH minuses. What is my pH?
It will be lower than 7.
Lower than 7 because I'm generating H plus. Okay, I'm going to stop this for a second because I want to shove in a slide. What happens if I have PW? Weak acid, weak base. What would you expect that pH to be? My acid isn't generating H plus, and my base isn't generating OH minus. What would you expect the pH to be?
Is it 7?
They cancel each other out. It should be about 7. On the other hand, I have I think I said X. Strong conjugate acid, strong conjugate base. The M is generating H plus. My X is generating OH minus. Am I going to have, what pH am I going to have for that, Natalia?
Excuse me, I didn't hear the last part.
My M generates H plus and my X generates OH minus. What is my pH going to be?
Neutral as well because you're generating both.
Absolutely. It's going to be neutral as well. So what makes an acid, what makes a salt an acid or a base? Basically, you have to look at the Ka values. If Ka equals Kb, we've got a neutral. The salt is neutral. If Ka is greater than Kb, it's acidic. If Kb is greater than Ka, it's going to be basic. So remember, this is not the Ka of the weak acid. This is going to be the Kb of the conjugate base. Now, I'm going to make this a little bigger. I have a series of acids and conjugate bases. All right. Now, my conjugate bases need a Kb. Where did the Kb come from? I have the Ka of the solution. I know that Ka times Kb is equal to Kw. So literally speaking, if I have HF and its Ka is 6.8 times 10 to the minus 4th, I take my Kw 1 times 10 to the minus 14th, divided by my Ka. That's how this number got generated. All right. So let's think about this. I have HCO3. That can be an acid because it can deliver that H. Its Ka is 5.6 times 10 to the minus 11. If I have that in a salt with F minus, now let's go with NH3. Which is larger, the Kb or the Ka?
KB.
So is it going to be basic or is it going to be acidic?
It's gonna be basic.
Everybody understand that? Any questions on that? Okay. Athar. I have a salt. The salt is ammonium formate. My Kb of formate is 5.55 times 10 to the minus 11th. My Ka for ammonium is 5.68 times 10 to the minus 10th. Is ammonium formate going to form an acid or a base solution?
Just can you repeat the last part? Did you say the format?
If I make a salt, ammonium formate, is that going to develop a solution that's acidic or basic?
Basic.
What is bigger, Ka or Kb, Ethar?
Oh, KB.
Kb is bigger, 10 to the minus 11th is bigger than 10 to the minus 10th. It's kind of
No,
something
sorry.
you got to wrap your head around.
So the Ka is bigger?
Ka is a bigger number, so Ka is bigger than Kb. Is my solution going to be acidic or basic?
Acidic.
Slightly acidic because these numbers aren't too far away from each other.
Mm-hmm.
Jessica, acetate and methylamine. Acetate has a Kb of 5.55 times 10 to the minus 10th. Ka of 2.27 times 10 to the minus 11th. So if I put them together, I know you've already answered, Jessica. I'm doing this for the benefit of others. If I put the anion and cation together and make methylamine acetate,
Okay.
is it going to be a basic solution or acidic?
Basic.
Why?
Because the basic has a bigger number.
The Kb is a bigger number than the Ka.
Yep.
Okay. Manual. Manual?
Yes, I'm here.
I have bicarbonate hypochlorite as my salt.
Okay.
Is my solution going to be acidic or basic or something else?
I'm gonna say slightly basic or neutral.
Yep.
'Cause,
Slightly basic.
Okay.
Very, very, very slightly basic. As a probability, you wouldn't be able to determine. It's probably going to give you a pH of 7. Okay.
Yo.
Now, how are we going to determine the pH of a solution with an anion acting as a base? Find the pH of a 1.4 molar sodium benzoate solution. The sodium benzoate completely dissociates. Sodium has no acid or base properties. The Ka of benzoic acid is 6.5 times 10 to the minus 5th. That's a Ka. We want to know benzoate. Benzoate is a conjugate base. So it's going to have basic properties. Can I use a Ka with a conjugate base?
You cannot.
Cannot. So I have to change the Ka to a Kb. I'm going to use the ice diagram to determine my OH minus. And then just like we did with the weak base, we're going to determine what our pH is by pH plus POH is equal to 14. That's the strategy we're going to do. Again, I've got a conjugate base. I'm making OH minus. I have to use a KB. Ka plus Ka times KB is equal to 1 times 10 to the minus 14. My KB is going to be equal to 1.5 times 10 to the minus 10. Are you with me so far? Set up my ice diagram. My benzoate was 1.4 molar. I make X benzoic acid back from that, XOH minus back from that. I'm going to stop the slideshow here. You don't need to know. You don't need to know what the exact formula is. You can kind of fake it. You can go benz. That's going to be your base. Plus H2O makes H benz plus OH minus. You don't need to know what the exact formulas are. As a matter of fact, at this point, that would confuse the hell out of you. Just make up something. You know that it is a conjugate base, so just call it benz plus H2O. What I make is the weak acid H-benz plus OH minus. I'm going to assign equilibrium concentrations of X to H-benz and OH minus. And my benz is going to then be at equilibrium 1.4 minus X. Are you guys kind of starting to be able to do the ice diagram in your heads rather than placing it on paper like this? You should be at this point. So I know what my KB is. So my KB is going to be equal to X times X, or X squared, divided by 1.4, because I'm going to disregard my X. I solve for X. My concentration is 1.9 times 10 to the minus 5th. My 5% rule is satisfied. I have to remember my X is OH concentration, and I want the pH. So I'm going to take the negative log of my OH concentration. This gives me 4.72. Subtract the 4.72 from 14. My pH is 9.28. I told you it was a base. I gave you a basic pH, 1 higher than 7. Are we good, ladies and gentlemen? You have to understand something. Polyhydroxyl bases. By that, I mean when you have parentheses and the OH has a subscript on it. This means that those compounds contain more than one OH minus. What happens is they can dissociate in one step. In other words, if I have an H plus in search of an OH minus, it will just as easily grab it from BaOH taken 2 as opposed to BaOH plus. Did you understand what I just said? It doesn't matter whether I have BaOH plus or BaOH2. The H plus is going to grab an OH from either. It doesn't care. On the other hand, if I have an acid, a polyprotic acid, polyprotics mean that there is more than one proton that acts as an acid. If I have H2SO4 and I add 1 mole of water to it, if I have 1 mole of base and add that to 1 mole of H2SO4, I'm going to end up with 1 mole of water and 1 mole of HSO4 minus. Adding the base to an acid, you take the first proton off first. So if I add base to H2SO4, I've got to take all of the H's off H2SO4 before I can take an H off of HSO4. Does that make sense to you? It doesn't to me, but that's the way that it is. When I'm doing an acid, you take the first proton off of all of the polyprotic acids, and you are left with a monoprotic acid. You have to take them all off the polyprotic acids before you can take them off the monoprotic acid. And each H plus has its own Ka. I have sulfuric acid. If I have 2 molar sulfuric acid, I have 2 molar H plus 2 molar HSO4. It completely dissociates. On the other hand, my Ka for the second proton is 1.2 times 10 to the minus 2. H3O, H3PO4 loses its first proton immediately in water to form H2O and H2PO4. So if you have 3 molar phosphoric acid, you have 3 molar H2PO4 minus. My Ka for that is 7.5 times 10 to the minus 3. I take the second proton off. The Kas go up because it gets more and more difficult to take a proton off of the acid. And taking it off, taking the third one is even more difficult. With each succeeding proton that's removed, the negative charge on the molecule is increased. So because the negative charge is increased, it gets harder and harder to take the H away from the subsequent anion. Okay, I have a polyprotic acid problem. What's the pH of a 2 molar solution of sulfurous acid, H2SO3? My Ka of my first one is 1.6 times 10 to the minus 2. To take the second one off, it's 6.4 times 10 to the minus 8. Isn't this kind of like a stronger acid and a real weak acid? Treat it the same way you did for the strong acid and the weak acid. Disregard the weak acid and solve it. The number of H pluses that are pulled off from the second proton, that can be ignored. So I'm just going to set up my ice table with regard to the Ka, setting it up. Set up my equilibrium equation. I get 0.056 is equal to X. Uh-oh, my 5% rule. I get 28%. Hold on a second, guys. Sorry. I pulled my plug out. So basically, I can't disregard X in this instance. I got to go through and do the quadratic equation. And I get my pH of 0.92. Good place for us to stop for the moment. And apparently manual's already stopped. 5-minute break, okay, guys? I'll be back in 5. Okay, we're done here. Anybody out there? Got a whole lot of blank screens out. Has it been 5 minutes yet, guys?
I think, or almost, I think.
Almost, okay. I can wait a couple more seconds. You all can hear me though, right?
Yeah.
Yeah.
Benita, you out there?
Yes, I am.
I have to say this. Cute bow. You have no idea what I'm talking about, do you, Benita?
No, what did you say?
Cute bow.
Oh, my head wrap? Thanks. I was like, Bo.
Okay. Aether, you out there?
Yes.
Anaya? I'm sorry.
Yes, I'm here.
Hey. Jordan. Vanessa, you were here.
I'm here.
Natalia.
I'm here.
Sarah. Gianna. Jenna.
Here.
Jennifer. Jennifer. Manuel. You back, Manuel?
Yep.
Parker.
I'm here.
Cherie. Araceli.
Here.
Jessica. Saw you earlier, Jessica. Are you out there now? Okay. Keanu. Valeria.
Here.
Jenna.
Here.
Leonardo.
Here.
Natalie.
I'm here.
Satori.
I'm here.
Raylena. Rhea.
Here.
Emily.
Here.
Delexis and Ethan.
Here.
Okay. Okay, guys.
Did you call for Justin?
Possibly, maybe. Yes, I did and didn't get an answer, but now I do, so we're good. Okay. Last chapter, we dealt with acid-base equilibrium. The chapter before, we dealt with Le Chatelier. Now what we're going to do is we're going to apply Le Chatelier to aqueous equilibriums, aqueous acidic equilibriums. So we're going to talk about the common ion effect. You've already done that. We've done Le Chatelier. That's what the common ion is. We're going to talk about how you do buffers, what a buffer is, and how you make it. We're going to talk about the Henderson-Hasselbach equation, buffer range. Then we're going to get into titrations using pH meters. This means we're going to deal with pH curves. Guys, I've already talked about indicators with you, have I not? Correct me if I haven't, but that's where we went through the indicators and did the colors. And based on the colors of the individual indicators, you were able to tell me what the pH is, right?
Yes.
Okay, we're going to deal with ionic salts in solution. Some of them form precipitates, some don't. We're going to deal with something called the KSP, which is going to be how much of this salt dissolves as ions, and that's going to give you a constant. We're going to be able to predict when something will precipitate, and we may get into qualitative analysis, we may not. So if I have a solution of acetic acid by Le Chatelier, if I add acetate, doesn't Le Chatelier say the equilibrium moves to the left? Is that true, Anaya? If I add some C2H3O2- to this equation, doesn't it say I have too much acetate and it shifts left?
Yes.
Absolutely it does. So I've got to look at how that common ion affects my equilibrium. So what I'm going to do is I'm going to have a equilibrium reaction where I have a weak acid that's creating a conjugate base. And what I'm going to do is I'm going to add the common ion. My weak acid will produce a conjugate base. I'm going to add to that a salt of the conjugate base and see what happens to the pH. Basically what it means is if my sample doesn't want to analyze and I add a salt that does want to with the same ion as the first sample, it means it's going to be less likely to ionize than it originally was. Let's prove that numerically. Calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. The Ka for HF is 6.8 times 10 to the minus fourth. And that is my Ka expression. Now, I am not starting off with my H3O being 0 now. HCl totally dissociates. So if I have 0.10 molar HCl, this means I have 0.10 molar H3O concentration. When I set up my ice diagram, my HCl means that I start with 0.10 molar H3O plus. I have 0.20 molar HF. I start off with no F minus because the problem doesn't say that I have any F minus. Now, if my HF will produce X amount of H3O and X amount of F minus, it loses X amount of HF. So I have my equilibrium concentration of HF being 0.20 minus X, disregard X. My H3O is 0.10 plus X, disregard X. And my fluoride concentration still is X. I plug that into my equilibrium expression, and I get 6.8 times 10 to the minus fourth is equal to my H3O concentration times my F minus concentration divided by my HF concentration. I do this and I find that my X value is 1.4 times 10 to the minus 3 molar. Am I doing anything that's strange? The only thing I've done is I've started off with my H3O concentration being a value other than 0. That's all I've done here. All right, my F minus is equal to 1.4 times 10 to the minus third. my H3O is going to be 1.0 plus 1.4 times 10 to the minus third, which is equal to 0.10. So my pH is going to be 1. If I had no HCl, my equilibrium concentration would be, my equilibrium expression would be the very top line here. Remember, my X turned out to be 1.1 times 10 to the minus 2. That was the F minus concentration. When I saw, I'm sorry, I missed something there. When I solved my equilibrium equation for X, I ended up, the result is 1.1 times 10 to the minus 2. That is the F minus concentration. Compared with 1.4 times 10 to the minus 3 when I added the HCl. My concentration has decreased tenfold by adding the HCl. So mathematically, we've proven that Le Chatelier, by adding the HCl, we make less F minus. We have a problem. We make a solution. We add 0.30 molar acetic acid and 0.30 molar sodium acetate to enough water to make a 1 liter solution. Okay, we have a weak acid that has a strong conjugate base. We're sharing the acetate ion. Our common ion, sodium acetate, acetic acid. Acetate is our common ion. We're going to determine the major species, determine their acidity or basicity. We're going to determine what the important equilibrium is, determine the H plus, which determines the pH. We're going to do the ice diagram and then calculate the H plus. My equilibrium, my overall equilibrium is acetic acid reacts to make H plus and acetate minus. If my initial acetate is 0.30, if my initial acetic acid is 0.30, then I have 0.30 minus X. I'm going to disregard the X. 0.30 plus X. I'm going to disregard that X. I set up my equilibrium equation, and lo and behold, my H plus concentration and my acetate concentration being 0.30 and my acetic acid concentration being 0.30, that's going to cancel out. Remember, I am crossing out the X's. So 0.30 over 0.30 cancels out, and my Ka is going to be simply equal to my H plus concentration. I'm simply going to take my value of my H plus, take the negative log. That's going to give me my pH. Questions, ladies and gentlemen? We've earlier done this. And when we have the 0.30, when we have a 0.30 molar solution of acetic acid, we calculated that pH to be 2.64 when it doesn't have any acetate. When it has acetate, we have decreased the H plus as we would expect. What is the pH when we add 0.085 nitrous acid with 0.10 molar potassium nitrate? I'm starting off with my nitrous acid concentration and my NO2 concentration. I take X away from my nitrous. I make XH3O. I add plus X NO2. So I have my equilibrium concentrations. Plug that into my equilibrium equation. I get that my H plus concentration is equal to 3.82 e to the minus fourth. Questions, ladies and gentlemen? Are we sick of ice diagrams yet? Ether, are we good? Leonardo, we good? We understand? Okay, guys, video up, or I'm going to, do you want me to call the roll again? Thank you. Manuel, Valeria, Sachari, Vanessa. I need you to video up. Thank you. I need to understand if you're understanding what I just did. Does it make sense to you? Does it make sense, guys? Anaya? Anaya, shake your head, do something. Put your finger up. Good? All right. Parker, we good? Araceli, we good? Does it make sense, guys? All right. Let's talk about what buffers are. By definition, it's a solution that doesn't change pH. Even if you add acid or base to it, it's not going to change its pH. Those of you that are going on in the medical field, it's a very, very critical thing. If the pH in your blood changes by 0.01, you die. So it's the buffer situation in your bloodstream is extremely critical because the pH will allow an oxygen to be released from what's the iron compound? What's the iron compound in the blood?
Hemoglobin?
Thank you. Thank you. The pH is going to allow the oxygen to be released or gathered in by the hemoglobin. The change in pH will allow the oxygen to release or to be gathered in. So if this pHs aren't right in these two different locations, you're not going to have a transfer of oxygen when you need it. So a buffer solution, if you have a high concentration of a weak acid and its conjugate base, you make a buffer. You can make a buffer with a weak base and its conjugate acid. This is how you make a buffer solution. Now, if you have a strong base will react with the weak acid to make the conjugate base. So if your strong base has a smaller quantity than the quantity of your weak acid, in effect, you are making conjugate base from your weak acid, but you still have some weak acid left. This also will make a buffer. Or if you have a strong acid with a weak base, the strong acid reacts with the weak base to make the conjugate acid. They're designed to hold the pH to a constant value. So let's consider let's see how they work. If I have my salt, salts as a general rule dissolve in water. They dissolve in water to make a cation and an anion. Now, if I have a weak acid, and that weak acid has a common ion with the salt, this means my equilibrium goes in the reverse direction because I have too much A minus. So if it has too much A minus, it's going to eat up any H3O plus. On the other hand, if I add the weak acid to it, because I have a strong H3O and because I have A minus, it kind of pushes it back in the opposite direction. So it kind of forces the reaction to keep its H3O plus under control. So I have my equilibrium expression up here. Sorry. I get very little A minus from the conjugate. If I have HA in solution, I'm generally putting in much more of the acetate from the salt than I am generating it from the acid. Most of the conjugate base comes from the salt and not the weak acid. So basically, if I have the initial concentration of the salt, remember, that's my conjugate base, and my initial concentration of my acid, I can derive something called the Henderson-Hasselbach Equation. All right, I've got my equilibrium concentration, so my Ka is equal to H3O times A minus concentration times my HA concentration. If I take the pH of both sides and rearrange, if I rearrange the equation, take the pH of both sides, then I'm sorry, take the negative log of both sides, I get the negative log of Ka on the left, which is the pKa. I get the negative log of H3O on the right, which is my pH, plus the negative log of A minus over HA. I rearrange this, and I get my pH is equal to pKa plus the log of my conjugate base over my acid. The conjugate base, remember, is my anion concentration. Now, a buffer is going to be useful when it's going to be most useful when the concentration of the acid and the base are real close to one another. Let's look at the Henderson-Hasselbach. What happens when the base concentration equals the acid concentration? What is that ratio, base to acid then? If the concentrations are equal, now concentrations aren't equal, what is concentration of base divided by the concentration of the acid? Araceli. If the concentration of the base equals the concentration of the acid, when I divide them, what does that equal?
Is that equal? But is that like equilibrium?
Nope, we're not talking about that. I'm just saying my concentration of base equals my concentration of acid, Araceli. if I divide the concentration of base by the concentration of the acid, what number do I get? If they're equal,
1.
I get 1. What's the log of 1?
0.
0. Yeah.
So if my base concentration equals my acid concentration, I've got the log of 1. This term goes to 0. My pH is equal to my pKa. As a matter of fact, that is how they determine pKa. They will take a buffer. They will take a conjugate base and a weak acid. Make sure that the concentrations are equal. They will put it into a pH meter. They will read the pH. pH is equal to the pKa at that time. So therefore, they determine the Kas by taking that pKa and raising 10 to that power, negative power. So a buffer is most useful when the pH is close to the pKa. So this means that the concentration of the conjugate base has to be real close to the concentration of the weak acid. Now the capacity of a buffer is the amount of acid or base that is added before a significant pH change is observed. It's equal to the amount of acid or base needed to change the pH by 1 pH unit. That is what the capacity is defined at. It's the amount of the acid, of strong acid or base that's needed to change the pH of the buffer by 1 unit. Rule of thumb. The moles of the conjugate should be equal to or greater than the moles of the weak acid. The moles of the conjugate must be equal to or greater than the number of acid or base you're going to add. Just a general rule of thumb. Henderson-Hasselbach problem. How many moles of ammonium chloride must be added to 2 liters of amine to form a buffer whose pH is 9? Assume the addition of NH4Cl does not change the volume of the solution. My Kb of ammonia is 1.75 times 10 to the minus fifth. Henderson-Hasselbach. I need to know the moles of NH4Cl that must be added to 2 liters. I got to plug the values in to the Henderson-Hasselbach. So that means I'm going to need the pKb. I also cannot deal with a pH and a pKb. I have to either change the Kb to a Ka or the pH to an pOH. So if my pKb is equal to 4.75, my pKa is equal to 9.25. Substitute this into my Henderson-Hasselbach. The pH I want is 9. I just determined what the pKa is. Subtract the pKa from the pH, I get a negative 0.25. In order to get rid of the log term, I have to take 10 raised to the minus 25 power. 10 to the minus 25 is equal to 0.562. that's equal to my concentration of my NH4 divided by my NH3. So my NH4 concentration needs to be 0.0562. I need 2 liters of it. So my molarity is moles per liter. I multiply it by 2 liters. I need 0.112. Now you know how to make a buffer solution. Let's go back. First thing, I can't relate a pH to a KB or a pKb. So I either have to change the pH to pOH or the KB to Ka. I chose to change the pKa to pK. I chose to change the pKb to pKa. So my Kb is 1.75 times 10 to the minus fifth. My pKb is a negative log of that number. My pKb is 4.75. This makes my pKa 9.25. I substitute that into the equation and I solve for the ratio. The ratio is equal to 0.562. But I know what my concentration of my ammonia is. It said in the problem, it was 0.10 molar. So I plug that number into the expression. I get the molarity of my NH4 plus. I need 2 liters of the buffer. So I multiply my concentration by the volume. This gives me the moles of my NH4 I need to add. Questions, ladies and gentlemen? Hey, at least it's not a nice problem. What's the pH of a buffer? That is 0.12 molar in lactic acid and 0.10 molar in sodium lactate. My Ka for lactic acid is 1.4 times 10 to the minus fourth. Natalia, you're yawning too much. That's my Henderson-Hasselbach. pH is equal to pKa plus the log of base over acid. Natalia, do I have the same amount of conjugate base and acid?
No.
No, I don't. So I have to figure that out. Remember, base goes on top of weak acid. So which number of the concentrations goes on top of which other number?
Wait, so the weak acid goes on, wait, sorry. Oh, so it would be 0.10 over 0.12.
Exactly. And I also have to take the negative log of the Ka to get the pKa.
Mm-hmm.
Who said what? Come on, who said what? This is my Ka. I need to take negative log of my Ka to get my pKa. So that's where the 3.85 hooks in. I take 0.10 divided by 0.12. That value is 0.833. I take the log of 0.833. I get a negative 0.08. I simply add negative 0.08 to my pKa. That gives me 3.77. That is my pH of that buffer. Questions, ladies and gentlemen? When you add a strong acid or a strong base, basically it's safe to assume that that strong acid is totally consumed. Strong acid or strong base get totally consumed in the reaction, and you end up making the weak acid or weak base from that. Okay, I have a buffer of 0.30 molar acetic acid and 0.30 molar sodium acetate. I add 0.020 moles of OH, strong base. The strong base will react with the acid. Now, if I react the OH with the HC2H3O2, I make NaC2H3O2. So if I add my NaOH to my acetic acid, I have decreased my weak acid by, decreased my weak acid by the concentration of my strong base. My strong base completely reacts with my weak acid. So now I've taken 0.02 away from my weak acid. Its concentration is now 0.280. But when I've reacted the base with the acid, I have made the conjugate base. So that 0.020 gets added to the conjugate base. Similarly, if I have a buffer and I add the H+, the H+ is going to react with the conjugate base, which is the sodium acetate. So the sodium acetate's concentration goes down and the acetic acid's concentration goes up. Using the HH equation, I can determine the new pH of the solution. If I wanted to do this, and it's always dangerous when Mr. Popovich goes out and ad-libs. If I wanted to do this, gotta find out where I was. There we were. Thank you. If I do this, the pKa of acetic acid is 4.74. So if I add that much base to my buffer, I get, why is this not working? Thank you. And this is how you determine if you have exceeded the capacity of your buffer. What I did was I added 0.02 of my base to my buffer. This changed my concentrations to 0.280 for my weak acid and 0.320 for my conjugate base. I put the pKa in and the log of the two concentrations. This means I have a new pH of 4.80. Have I broken my buffer? Does it change it to a value of 5.74 or greater or 3.74 and lower? Did I change it by that much? The question is, did I break the capacity of the buffer? Remember, is it plus or minus 1 pH unit beyond did I break the buffer?
No.
No. Let's change this around a bit. Say I add 0.10. If I add 0.10 of my base, this changes this to 0.4 over 0.2. In this case, I get a negative so I should be I get a positive 0.301. So this ends up being 5.0 5. Did I break the buffer yet?
Yes. Wait, no.
I have to be, in order to break the buffer, I have to be at a pH of 5.74 or greater or less than 3.74. Okay? Say I add if I add 0.25 molar NaOH, this means I have 0.55 and 0.05. Remember what I'm doing. Remember what I'm doing. My original solutions are 0.3 A minus and 0.3 HA. So I'm subtracting 0.3 minus 0.25 equals the HA. 0.3 plus 0.25 equals A minus. Because the strong base completely reacts with the weak acid to create more conjugate base. In this case, this ends up being the log of 11. Did I break the buffer?
Yes.
Now, remember what we said way back when. And I got to find it again. For buffer capacity, number of moles of the conjugate base must be equal to or greater than the moles of acid or base you're going to add. Going back here, is 0.25 close to 0.3? Is 0.25 close to 0.3?
Yes.
Thank you. Guys, yeah, I realize my sitting here talking about equations isn't the most exciting thing you have to deal with. However, you got to pay attention to this crap. So the 0.25 is real close to the amount of your conjugate base. What that means is that I'm going to be real close to breaking the capacity. And by using the Henderson-Hasselbalch, we just proved that. When we added 0.1, that wasn't enough to break the buffer. 0.2 wouldn't be enough to break the buffer. 0.3 is. So basically, at that point, there is no more conjugate base. There's no more A minus, or I'm sorry, there's no more weak acid. The strong base has effectively taken away all the weak acid that we have. Therefore, when I keep on adding base to it, the pH is going to go up rapidly. The same thing would occur if I was adding H plus. If I'm adding H plus, I'm depleting A minus. When I get close to the concentration of the A minus with the concentration of the acid, at that point, I will be just adding H plus, and the pH is going to go down rapidly. I just did a calculation like that. Okay, I went through that exhaustively. Do you want another calculation to determine whether you break the buffer? Or are you good, guys? Talk to me. Tell me what you need.
I'm good.
I think it would be helpful.
It won't take that long. I got a buffer made by 3 molar acetic acid and 3 molar NaOH. The pH of the buffer is 4.74. Calculate the pH after 0.020 molars, 0.020 moles of the NaOH is added. Henderson-Hasselbach. Before reaction, I had 0.30 acetic acid, 0.30 acetate. If I add 0.02 to each one of those, I create the new concentrations. I plug those values into the Henderson-Hasselbach, and I've changed the pH only about 0.06. When we titrate, guys, ladies and gentlemen, what we're doing is we're taking a known concentration of base or acid and we slowly add it to the opposite. So if I have a known concentration of base, I'm going to add it to an unknown acid. And I am going to monitor the pH with that. I've talked about indicators, so I'm not going to go through that again. Now, if I do it with a pH meter, we're going to talk about titration curves now. Different subject. If I am titrating a strong acid with a base, understand the semantics here. I'm trading the acid with the base. What am I adding to what? Jessica. If I titrate the acid with the base, what am I adding? What does the sentence say?
You're adding the base?
I'm adding the base to the acid. So Jessica, if I'm adding the base to the acid, would you expect my pH to be low or high?
High?
I'm taking the pH of the solution that I'm adding the base to. So should my pH be high or low?
Low.
It's going to be low because I'm taking the pH of basically pure acid before I add any base, then I'm adding base to it. The pH of a strong acid is going to be very low, around 1 or lower.
Okay. Yep.
As I add base to this, let's do this in the slideshow. Why is this playing games with me today? Sorry. Okay, this is the curve. You're saying this is my curve. My y-axis is going to be pH. The x-axis is going to be milliliters of NaOH. As Jessica determined, my pH is going to be low at first because I've added no base to my acid. If I've got a strong base with a strong acid, then the pH is going to gradually increase until I get to the point where I've almost used up all of my acid. If I've used up all my acid, all I'm doing from that point is detecting the OH of the base I'm adding. So it's going to go up almost vertically at that point to the point where it then starts to even out and becomes steadily even at that point. When I've reached this point, I'm pretty much just getting the pH of my base at that point. Again, this is a titration curve of a strong acid with a strong base. Fairly even increase till I get to the point of no return. Then it goes up vertically. Then it eases off until I get a pH of the base. If I want to determine the equivalence point, I have to determine what my high and low pH values are. So if I've got this value, my high value is about a 12. My low value is, we're going to call this 2 just to make it easy. So if my high value is a 12 and my low value is a 2, what I'm going to do is I'm going to average those. 12 plus 2 divided by 2 is 7. I'm going to find my pH of 7, which is the average between my high and low pH. I'm going to take it over to the curve, and then I'm going to drop it completely down. That tells me it took 50 milliliters of NaOH to reach the equivalence point of this particular titration. If I knew the concentration of my base, I could take my volume, 50 milliliters, times the concentration of my base. That would give me moles of base. I would then take my moles of base, multiply it by the molar ratio to get the moles of acid, and divide by the original amount of acid I started with. Nothing more than the same titration problem you had when you were using an indicator. I've got my volume of base. I've got my concentration of base, and I know what my original volume of my acid is. So I'm going to get my titration milliliters by taking the high and low pH values, averaging them. From the pH, I'm going to move over to the curve, and then I'm going to take it straight down. That's the volume of base I needed to neutralize the acid. Again, just like a normal titration, I'm talking about moles of H3O and moles of OH minus. If the moles of H3O delivered by the acid equal the moles of OH minus delivered by the base, I can shorten the equation to MAVA equals MBVB. If you don't know how or why this works, then take it the long way. Convert to moles of your base first, then use the molar ratio to get moles of the acid, then divide by the milliliters of the acid. Second curve. I've got a weak acid with a strong base. Manual. I'm starting with the weak acid, and I'm titrating it with a strong base. What am I adding to what?
You're adding, it's a strong base. I'm not too sure. I'm sorry.
You got to understand the English behind this. If I'm titrating the acid with the base, then I am adding the base to the acid. Okay, Manuel, you got that?
Okay.
So if I'm adding the base to the acid, am I starting off with a low pH or a high pH?
High pH.
I'm adding the base to the acid. So I start off with, am I measuring the pH of the acid or the base?
The acid.
So what's the pH? Is it going to be low or high?
Lower.
All right. Now, $50 million question. Is the pH of the weak acid going to be higher or lower than the pH of the strong acid?
Is the pH going to be higher or lower?
Higher.
Higher? Yeah, higher. Sorry.
It's a weaker acid. If it's a weaker acid, it has less H3O concentration, right?
Yep.
Less H3O concentration, pH is going to be higher. So if you remember, the strong acid started at about 1. This is starting out a little higher, 2 to 3. Now, what happens as I add base? As I am adding base to this, I'm adding a base to a weak acid. Am I not making the conjugate base?
Yes.
Guys, it's just not limited to just manual at this point. I'm adding a strong base to a weak acid. I am making my conjugate base. I'm making a buffer because I'm increasing my conjugate base, and I've got my weak acid already. I am making a buffer. So what happens is you go through a more gradual increase in the pH as you add the base. This region from about 20 to about 40, this is generally called the buffering region. Look at this increase, gradual increase of pH versus milliliters of NaOH versus the strong acid. Do you see that this pH change is much more? That doesn't make sense. This is more gradual than the other one is. Does that make sense? Did you see the slope of the strong acid isn't as steep as this is? The strong acid was kind of almost flat. This one is going up at a higher rate. That's because we're adding base in. We're adding the conjugate base in there. When I had a strong acid, that meant that I have a weak conjugate base. There is no conjugate base that's really being added. It's a strong acid. So I don't have this steeper pH because I'm not getting any conjugate base there. But like the strong acid, when I get close to using up all of the weak acid, at that point, I'm just adding base, and I get to the point where I am just adding base, and I get the pH of just the base. Does anybody see any difference? What's the difference after the equivalence point of the titration curve of a weak acid with a strong base versus a strong acid with the strong base? Do you see any difference from the equivalence point on? Kind of get a mental picture of that versus That. Is there any really difference after the equivalence point? Does anybody see any difference? What's different about these two pictures?
Equivalence point for this one was within like the violet strip, and then on the other one it's below the violet strip.
Okay, that's a good point. Good observation. That is an excellent observation. And I'll address that in a second. But what I'm saying is once we get past the equivalence point, didn't it go up rapidly, kind of ease off, and then get to the final pH? There is no difference in the curve of a weak acid with a strong base and a strong acid with a strong base once you get past the equivalence point. Everything happens before the equivalence point because logically, if you think at the equivalence point, I've used up all of my weak acid. The only thing I'm doing at that point is adding base. Now, you brought up a point. Look at where the equivalence point is for the weak acid with the strong base versus the equivalence point for the strong acid and a strong base is about 7, pH 7. Why is the equivalence point of the weak acid higher than 7? Am I not just adding acid and base together? And if they're equal, then shouldn't it be 7?
It should be leaning more towards the base since you have a bigger amount for the base rather than, and the acid is lower.
I'm adding the molarity. Say I have 1 molarity weak acid and 1 molarity strong acid. I still will get the equivalence point being at a higher pH for the weak acid than the strong acid. The question I have is why? Think about it. First person that comes up with the answer on Thursday gets an extra credit point. It's 12:20. We got to leave. We have to part company. I know you're just enthralled with all these calculations we're doing. Questions? Questions, guys?
You took attendance, right?
Yep. Took it twice, as a matter of fact.
Okay.
Look this stuff over, guys. Question?
I don't have a question about this. I have a question about the lab.
Okay,
today.
go ahead. Ask quick. Ask quick. Go ahead.
Is there a pre-lab?
No.
Okay, so you just want us to come with our proposals then?
That's it. I think that if you looked at the assignments tonight, I think that's all I told you to bring today.
Okay, just double checking.
What you have to bring on Thursday is both reports that were due last week. I'm sorry, both reports from what you did last week. Okay, that is due on Thursday.
Okay.
Because of the proposal, I just let you deliver last Tuesday's lab on Thursday. Fair enough?
Yes, and the lab report for equilibrium, that's due Thursday too, because in the
Both of them are due on Thursday.
Okay, cool.
Okay? Talk to me then. I could be talked into delaying it. But you're still going to have to do it one way or the other. Anybody else have any other questions? I will see you on Thursday, guys.
Thank you. Have a good day.
Take care.
All right. Bye.
Valeria, have you skipped out on me? Valeria. Thank you.